So energy use in the environment. I'm going to go through this pretty quickly. I think it's a useful thing to talk about, but I'm not going to test you on this. So, kind of astounding, each person in the United States uses over 100,000 kilowatt hours of energy per year. Much of that comes from the combustion of fossil fuels. Pure carbon, combusting, methane, octane, these release different amounts of energy. So standard heats of reaction. One way to evaluate a fuel is by looking at how much heat is released compared to how much carbon dioxide is produced. Because carbon dioxide is a greenhouse gas and can contribute to global warming. So this is what they're talking about with your carbon footprint. So better fuels have higher ratios of heat to carbon dioxide production. And you can't just look at delta H, because here this is 5,074 kilojoules, but it's 8 moles of carbon dioxide, right? We can compare these pretty easily because both of these make 1 mole of carbon dioxide. So methane releases 802 kilojoules for every mole of carbon dioxide produced, whereas pure carbon is only 393. So methane is going to be a better choice in terms of getting us the energy we need and minimizing the production of carbon dioxide. Just quickly, we could take that 5074 and divide by 8 and find out that that one's negative 634. So it's kind of in the middle. So this would be negative 634 kilojoules per mole of CO2. That's one way to evaluate fuels. Yes?
So is that the difference between gas and regular gas?
That is one of the differences between premium and regular gas. It's actually quite complicated. Yeah. So fossil fuels, come from ancient life. They cannot be replenished. At our current rates of consumption, the prediction is that the oil and natural gas supplies will be depleted in 50 to 100 years. And this is showing where those are used: residential, commercial, industrial, and transportation. Sort of, for your information. This is a table showing energy production or consumption, over the course of time since 1950. So this is energy from petroleum, from natural gas, from coal, renewable energy, and nuclear electric power. So overall, everything's been increasing. What are the effects of combustion products? Just the burning of methane produces carbon dioxide and water, and those are not considered hazardous, but you don't burn just pure methane or just pure octane. Our fuels have other things in them, impurities and additives, and so those are going to release other things. So fossil fuel emissions contribute to air pollution. They contribute to acid rain and to global warming. Levels of those pollutants are decreasing because of the Clean Air Act. Things are going down, getting better. This is showing that from 1980 to 2013. SO2 levels have dropped by 81%, carbon monoxide by 84%, NO2 by 60%, and ozone by 33%. So that's good, it's encouraging. Climate change. Carbon dioxide is a greenhouse gas, and so it is one of the gases that holds energy around our planet. We need greenhouse gases because otherwise our planet would be too cold for life. But if we have too much, then it's going to get too hot for life. CO2 levels have been steadily increasing. Current observation is that average global air temperature has risen 0.7 degrees in the past 100 years. And the warming effect could get worse if we can't level off our CO2 production. So this is showing carbon dioxide concentration in parts per million from back in the 1800s up to, it's like about 2017 maybe. And we can see it was going up and up and up, but then it's risen sharply in the last 40, 50 years or so. So global warming can lead to a lot of problems. The thing I'd like to point out about this is that the Earth has long cycles of climate change. And so the average temperature one year and the average temperature the next year, we don't even reasonably expect them to be the same. And so saying that there's been a 0.7 degree increase over the past, how many years, scientists disagree about that exact number because of how those things are measured. I mean, how do you measure the average global temperature? How do you measure the average global temperature back in 1800, right? The data available is limited. So there's a lot of extrapolation that occurs, and some of it's very valid, and some of it maybe not so valid. So I am not at all saying that I don't believe in global warming, but I'm going to say that there is room for debate. When you're given numbers, you have to question them because data can be manipulated to show almost anything that you want. Okay, so let's do this example. What mass of carbon dioxide in kilograms does the combustion of a 15-gallon tank of gasoline release into the atmosphere? Assume the gasoline is pure octane, and then it has a density of 0.7 grams per milliliter. Yikes. Where do we even start with this? Scratch it and go on to the next one. It's tempting, believe me. Well, we've got octane burning, right? Producing CO2. So is that a chemical change? Chemical reaction occurring. How about we start by writing a chemical equation? So C8H18 is going to react with what? Oxygen and form CO2 and water. Because that's combustion. So we need to know, we can figure out, we've got 15 gallons, we've got a density, we can figure out the mass or the moles of the octane, but how many moles of carbon dioxide are produced for each of those? Well, we got to figure that out. So we got balanced equations. So there's 8 carbons here. Let's put 8 carbons over there. Hydrogens, there's 18 here, so we need 9 water molecules. And then we've got 2 times 8, we've got 16 here, and 9 there. Oxygens, right? And so that adds up to 25. So we could balance this by doing 25 over 2. So we could multiply by 2 and clear the fraction. Do we have to? No. What we need for this problem is the relationship between octane and moles of CO2. It's 1 to 8, and so we could use it just like this. We're talking about combustion, so we need a delta H for this, right? So that we can figure out, no, we don't. Never mind. We're not talking about energy. We're talking about mass of CO2. Okay, so we know we have 15 gallons. Well, that's awkward because that's one of those English units. And we're looking for how many kilograms of CO2. And we're given a density of the octane. 0.70 grams over milliliters. So regular stoichiometry, grams to moles to grams. But we want to end up with kilograms, so we could add one step at the end. And then we're not starting with grams, we're starting with gallons. So we've got gallons. We would need to get that into milliliters, and then we can get to grams. Fun, right? Not on Monday morning, it isn't. So gallons of octane, we're going to convert that to milliliters. We got gallons on the bottom. And then we're going to use our provided density to get to grams. And then we have to go to moles of the octane. And then we need to get to moles of CO2. And grams of CO2. And kilograms. Isn't that fun? Well, let's start with things that we know. Mole ratio. 1 mole octane, 8 moles CO2. So 8 moles of CO2 for every 1 mole of octane. The density was given to us, 0.7 grams per milliliter. So here's grams and milliliters. So I'm going to put the 0.7 with grams, 0.70. Kilograms to grams. Kilo means 10 to the 3. So I'm going to put 10 to the 3 where the kilo is not. 1 kilogram is 1 times 10 to the 3rd grams. This is a molar mass. We can calculate that, but I have it memorized, 44.01. I don't have the octane one memorized, so we will have to calculate that. 8 times 12.01 plus 18 times 1.008. $114.224. So 1 mole of octane weighs 114.224 grams. And I need gallons to milliliters. So that would, how you get there depends on what information you have available. So this isn't an exam. Hey Siri, how many milliliters in 1 gallon?
1 gallon is 3,785.41 milliliters.
Let's go. 3,785.41 milliliters is 1 gallon. Now, on an exam, you might have to do more calculations than that. So now we've got this big old mess. So 15 times 3,785.41 times 0.7 divided by 114.224 times 8 times 44.01 divided by 1 EE3 equals, how many sig figs? 2. 122.5 kilograms. So that would round to 120 kilograms of CO2. It's a lot of kilograms. It's over 250 pounds of CO2. Yes? Pardon me? We actually didn't use the 25 over 2.
No, I mean, where was it given?
Oh, where did it come from? So when I was balancing this equation, I balanced the carbons and the hydrogens, and I ended up with 8 and 9 here. And then I added up how many oxygen atoms do I have on the right side, and there were 25. And over here, the oxygens are coming in pairs, so I need 25 halves. Normally, we would multiply everything by 2 to clear the fraction, but it's not absolutely necessary. Any other questions? So, renewable energy is a wonderful idea. The greatest supply of energy that's unlimited is the sun. So there's a lot of new technologies that are taking advantage of the energy that's coming from the sun. Solar power is becoming a lot more common, and it's a great idea here in the Central Valley where, most of the time it's sunny. Solar energy can be used to decompose water into hydrogen and oxygen, and then the hydrogen can be used as a fuel in a fuel cell. So you maybe have heard about hydrogen-powered cars. So that's awesome. The problem is, where do you get the hydrogen? Well, it comes from water, but it requires energy to produce the hydrogen. So if you're using, fossil fuels to generate the electricity needed to make the hydrogen, then your hydrogen-powered car is not helping the environment at all. But if we can use solar energy to do that, we could make hydrogen without using or producing any pollutants, and then when the hydrogen reacts in the fuel cell, reacts with oxygen and reforms the water. So that's a good thing. So other forms of solar power, hydroelectric power, where you take water that's falling and use that to turn turbines, and wind power.